So now I've done all the introductions, you'll be very pleased to hear, and I can move on to the actual program, and I'm going to ask Professor Ineke de Moortel to give a talk on the role of MHD waves in coronal heating. Go on, please. I'll show you in 5 minutes.
That'd be great. It's back up. Okay, thank you very much for the invitation. Although I was left wondering whether our founding members approve of the fact we're no longer meeting in a tavern. I'm going to talk to you, I'm going to put my own timer on here as well. I'm going to talk to you about wave heating in coronal loops and where we stand with that subject as I see it. I'm hoping I can go over this slide fairly quickly. It's a schematic picture of our sun with the hot core, the radiative zone, and a convective zone above that. But I'm going to be focusing on the sun's atmosphere. And in particular, I'm going to be mostly focusing on the outer layer or the corona of the sun's atmosphere, which I'm sure you all know that in common with many other stars is much hotter than you would perhaps expect from the surface temperature. Now, we know that a crucial agent in this heating mechanism is the magnetic field. We know that the magnetic field somehow carries the energy from the subsurface motions into the outer atmosphere. And what we need there is to create small length scales to allow diffusion to happen. Traditionally, coronal heating mechanisms have been divided up into two theories or two categories of theories. Theories based on slow foot point motions, generally thought of reconnection models, and fast timescales or wave-based heating mechanisms. Now, I'm going to be focusing my entire talk, apart from the very last slide, on the wave heating mechanism. Okay, so please don't think that's the only mechanisms we have. I'm just going to focus on that category. So what's the idea? The idea is that generally you shuffle these foot points around a little bit, waves propagate up, dissipate their energy, and you heat the solar coronal loops. And if only it was that simple. Now, wave heating theories have been around for a long time, and in fact, they were historically first suggested as heating mechanisms for part of the solar atmosphere. This is a paper from 1987, where J. de Villa suggested that resonant absorption, which I'll go on to explain, is a possible heating mechanism for the solar atmosphere. And there's a vast literature, which I am not going to address. I'm just going to give a very basic explanation of the two big heating mechanisms, or what traditionally were considered the wave-based heating mechanisms of resonant absorption and phase mixing. So what I'm going to do in the next few slides is explain those basic mechanisms, but really only on a cartoon level, so you have a picture of what they are, or at least what they mean within solar MHD wave theory. I won't go into the literature and all the developments. I'll then show you some examples of observations that have been interpreted as MHD waves in the solar atmosphere. And then I'm actually going to focus on how these mechanisms are problematic and what we can do about it by developing our models further. Okay, so let me give you a very basic explanation of resonant absorption. Imagine you have one of these coronal loops, just here, which we make easier in our models. We just straighten it out as a straight cylindrical flux tube. And if you imagine it's somehow hit by this, from its side, or actually from its foot point by an incoming wave, if there is a layer here where the density varies gradually between the interior density of our flux tube and the exterior density of the medium, then somehow, somewhere in this boundary layer, there will be a resonance point. Okay? And the idea is that all the energy is sucked into that resonant layer, which then means it'll sit on a very small length scale and allow dissipation to happen. Okay? So this is just, again, a schematic of all the energy being sucked into a very narrow region in the boundary of this loop. Okay, so that's a very basic picture of resonant absorption. And a similarly basic picture of phase mixing. Again, if you imagine this kind of curved line to be a gradient in the alphane speed, and just think of it as a gradient in the local density again, if you then generate a wave at the bottom of all these magnetic field lines, imagine all the field lines are just upward, but there is a density or an alphane speed gradient across the magnetic field lines, And waves on this side will propagate, well, if this is the density, they will actually propagate slower on this side and faster on the other side. So what happens is that the whole wavefront turns of phase mixes. And I've got a little animation here that illustrates that. Okay, so as the wavefront propagate upwards, you can see that they turn. And if you then look across the wavefront, whereas you had no gradient across the wavefront at the bottom here, by the time you come higher up, you can see that you've generated small length scales across the field. What that does is allow dissipation or enhanced dissipation to happen. And so in the region where the gradient is stronger, your wave is dissipated. Okay? And we know from the paper by Havarts and Priest in 1983 that this damping profile has a very characteristic e to the minus z cubed profile. Okay? So if this is the bottom of the loop, you drive the wave, and as it propagates upwards, the amplitude decays, the energy is dissipated with this characteristic e to the minus z cubed profile. So that is, I don't know, probably about 20 years of modeling of MHD wave heating mechanisms summarized in 2 slides and a couple of cartoons. But that's the basic mechanism. Somehow we try and get the wave energy onto smaller scales so we can dissipate it. Okay, so let me switch for a moment, and then I'll bring them back together, to observations of waves in the solar atmosphere. And I'll show you just a couple of examples to highlight what kind of observations we have and how they've been interpreted as waves. Okay, so this is not a comprehensive overview of observations of MHD waves in the solar atmosphere. So let me start by the chromosphere, the layer just below the solar corona. This is a picture, an observation taken in calcium-2, so about 10,000 degrees. So what you see here is just the lower end of coronal loops. And you can see that all these structures are constantly swaying. Okay? They're also related to spicules, which are kind of dynamic jets on the interface between the chromosphere and the corona, which I might come back to in the end if I've got time. But if we just look at those swaying motions, then actually it turns out that there's a substantial amount of energy within them. And Bartoppontjeau and colleagues did an analysis of this a few years ago and found that even if you only allow for a very small transmission coefficient into the corona, there is a lot of energy there. Okay? The energy here that they estimated is of the order of 100 watts per meter squared. For the quiet sun or coronal holes, that's about what you'd need to account for coronal heating. Okay? Now, of course, they're only talking about the energy flux. They haven't said anything about whether this flux can be turned into thermal energy, whether it can be dissipated in the right time and length scales. But certainly a substantial energy budget in these swaying spicules. So that's one example. Okay. Different type of example, still staying in the chromosphere. This is an observation by Richard Morton at Northumbria University and colleagues. And you can't really see it, but there's a thin black line across these 2 black structures. So there's these black bands here in the image, and then there's a thin black line across it here. What's on the picture on the right-hand side is the intensity in this thin black line and time. Okay, so hopefully you can see that. And what you can see is that these thin black structures both sway, they kind of go back and forth, but also that they change in width at the same time. And these authors suggested that that's a combination of both incompressible motions, the swaying back and forth, so that would be swaying kind of in this plane of the picture, and compressible energy, which is accounted for by this changing of the width of the structure. Again, by only assuming very small transmission coefficients, there is substantial energy in these combined motions that could possibly account for at least a significant part of coronal heating if we can get the dissipation in the corona right. Let's move to the corona. Again, we have observations of what we interpret as MHD waves. This is an image taken by the AIA instrument on board of SOHO. And what I'm showing here is intensity at about 700 to 1,000 to 1,000,000 degrees. Now I'm going to play the movie of this little sub-image, okay? This little sub-image just focuses here on the apex of the loop. The little bit on the left is just the intensity. The one on the right is intensity where some kind of smoothed average has been subtracted to enhance sideways motions. So if I play that, you can see, or you at least hopefully get the impression that this whole volume is kind of permeated by very small scale transverse, oh, I'm sorry, it's not looped, transverse motions. It's hard to see in the raw intensity, but if you look in this kind of enhanced intensity where the background has been subtracted, you hopefully agree that there's this constant, very small scale impression of swaying motions. Again, they analyzed it and compared it with Monte Carlo simulations. They found an energy that would be sufficient for quiet sun or coronal holes, but for active region loops, they actually found that there was almost an order of magnitude too little energy in these particular observations. Okay, these are only intensity observations, so all you're getting here is a swaying of that structure. And then one final example further out into the corona on larger scales. These are images done by the COMP instrument, which focuses on these large off-limb loops, so the disk of the corona itself is occluded. And what's shown in this animation is the Doppler velocities this time, so not intensities. Doppler velocities, and they've already been filtered in Fourier space to be focused on 3.5 millihertz, so roughly 5-minute periods. And if you try and focus on this kind of loop system at the bottom here, I hope that if you look at it after a while, you see that there's constant kind of white and black blobs propagating along these loops. Okay? So white and black here would correspond to blue and red-shifted Doppler perturbations that are propagating along this loop. Okay, so in this case, these would be perturbations in the plane, in the line of sight, so towards and away from you. Okay, so what did they conclude? Well, actually, they also had intensity observations, which I'm not showing you because there's nothing to see. The intensity fluctuations are very, very small. I mean, you can see the loops, but there's nothing there in the form of perturbations, or at least not very much. And all they found was these kind of small amplitude perturbations in the Doppler velocity, nothing in the intensity. And these authors actually interpreted this as propagating Alfvén waves, also because the propagation speed along the loops roughly matched the Alfvén speed that was expected. There was a lot of discussion in the literature about whether these were Alfvén waves or not, but that's not actually important for my talk. What is important is the graph on the right. Now, what this shows you is power ratio, and it shows you the power ratio between perturbations propagating up along the loop and down, so outward and inward wave power. And wherever the graph is colored predominantly red, there's wave power coming up from the loop foot point, but not down. And where it's kind of towards the blue, you've got more downward propagation. So what you can see, remember this was our loop system, is that essentially you've got upward propagating wave power on both sides. So what we're not seeing is the waves coming up and going down on the other side. And what they concluded from this is that there must be substantial damping of the wave power as the waves go along the loop. Now, we know historically that actually dissipation of wave energy is quite hard to do with those models that I described at the very start. So this is actually a surprise, because if you do this in terms of wavelengths of these waves as they propagate along the loop, you've only got 1 or 2 wavelengths to get this outward power damped sufficiently. Saying that there wasn't much power observed in these waves. Okay, so we're not interested as much in their power as what they're telling us about the actual damping mechanism. And then one final example. This is an example by Jonathan Thurgood, who was a PhD student, I believe, at Northumbria University at the time. And he looked at transverse waves in coronal plumes. So this is the disk sorry, this is the limb of the sun, and you see these faint structures here. Again, this is an intensity image where the background intensity has been subtracted. And if I play this movie, you might, although it doesn't show up very well on the screen, you might at least get a faint impression that all these structures are swaying a little bit. It's hard to see on that screen, I must say. The image on the right is again a time distance plot. Time is on the horizontal axis, and the distance is on the vertical axis. And the distance represents a cut along this first dotted line here, the lowest one. So if you plot the intensity along that line, up here, and then follow it as a function of time, you see all these very small swaying motions, but throughout time at different parts of this cut. So again, you get kind of ubiquitous, transverse, but very small scale swaying structures. The difference with some of the previous slides is that this is in what we think are magnetically open structures. Okay, so that was just a very quick kind of taster of the kind of observations we have of MHD waves in the solar atmosphere. Essentially what the last 10, 15, 20 years of observations have told us is that there's a substantial amount of wave energy throughout the solar atmosphere. And that's brought the community back to critically looking at MHD wave-based heating mechanisms. Can they actually convert all this wave power that we seem to be observing into coronal heating or not? And I'm going to try and address what I think are 4 fundamental questions. If these waves are to contribute to heating, then we need to convert that flux into actual thermal energy. Now, I'm going to show you that wave damping, as is sometimes observed in the observations, is not the same as dissipation. And if you don't have dissipation, you don't have any heating. That there are issues with the time scale of the dissipation mechanisms, and also that there are issues with their self-consistency. The traditional wave-based heating mechanisms make assumptions that they can't actually sustain without the addition of another mechanism. So I'll go through these questions in turn. Again, let me just emphasize that I'm going through these studies on a fairly cartoon level just to get through the talk. I hope you appreciate that our science is not entirely at cartoon level anymore. So let me just have a cartoon of what was actually a series of about 5 or 6 papers. We again have what's actually represented by these straight lines in the background, a flux tube. So just a straight cylinder with a uniform magnetic field throughout, both the cylinder and the environment. The cylinder is made by a density enhancement. And the density enhancement gradually, as represented by this blue line here, matches the enhanced density of the cylinder with the lower density of the external corona. Okay? So there's a layer here where the density changes gradually. If you now imagine that you just shake this flux tube at the bottom, you'll send up transverse waves. They'll propagate up along the loop. And by mode coupling, they will excite azimuthal motions in the boundary layer, in this layer where the density gradually changes. So as the waves propagate up, you get a change in the characteristic wave motion. Okay, they go from the kind of swaying motion. I really should have reversed these. This is the bottom and this is the apex of the flux tube. You really have a transverse swaying motion, low down, and as you propagate up, you get these kind of azimuthal motions in the boundary layer. And I'm going to play these movies. These movies come from 3D MHD simulations, where this is a cross-section through the density at the loop foot point, and overplotted, a little bit too small to really see in detail, of velocity arrows. And hopefully you can see, I know you can't quite see the arrows, but hopefully you at least can see that these are kind of a linear side-to-side transverse motion at the bottom of the flux tube. And then this is a cross-section again through the density. The density hasn't changed, but much higher up, as the waves have propagated up from the foot points. And again, hopefully you can at least get the impression that all the perturbation is now focused in this boundary layer here and has a torsional or an azimuthal character in higher up. What does that mean for the observations? This is a similar picture. It's essentially just showing you that the Poynting flux that went in the loop center at the bottom here is now sucked into this boundary layer between the two dashed lines. So what does this mean for our observations? Thank you. The observation showed a swaying motion, okay, from side to side, but this mechanism converts it into this kind of torsional motion, which is much harder to observe and which would not necessarily show up in the intensity. So we would observe this as wave damping, but it is not dissipation. Now, our chair has just highlighted that I need to speed up significantly. Timescales. Again, there's a lot of modeling behind what I'm summarizing, essentially just in this column, which is all I want you to focus on. The formulas are here for my solar colleagues who might recognize them, but please just look at these numbers. This work's been summarized by my colleague Inigo Aregui, and what he looked at was the typical timescales of damping as a ratio of the period and diffusion, okay? And what that's telling you is that a typical observation damps this swaying motion in, I don't know, about 13 or 3, but in a low number of periods, okay, depending on the assumptions you make about the loop structure. However, if you look at the diffusion time, this number is at least an order of magnitude, if not 2 orders of magnitude larger. So what that's telling you is that you wouldn't get dissipation or heating within the observed lifetime of the oscillations. Okay, let me touch on one more topic, and then I'll skip to some of the more modern models, and that's whether this mechanism is self-consistent. Now, from very basic scaling laws about the heating, radiative cooling, and thermal conduction, we actually know that regions where the density is highest require most heating. Okay, so if we think back about this kind of characteristic profile of the density that we seem to assume for coronal loops, the density is highest in the middle. Now, the wave heating mechanisms that I talked about at the very start are most effective where the gradient of the density is biggest. And that's not where the density is biggest. Okay, so the gradient of the density is steepest at the sides of the flux tube, and that's where the wave heating will be focused. But actually, we require we require most heating at the center of the flux tubes. And if we look at that, this is just again a result from the 3D simulations that shows you a cut through the loop, along the loop, and it shows you the increase in temperature, which is concentrated in this narrow shell at the edge of the region, and the density profile that would be associated with that would be peaking in that shell region, not where the assumed density profile peaks. And what that tells you is that the two are incompatible. Okay? So this assumed equilibrium that the wave heating mechanisms rely on is not self-consistently maintained by the wave heating mechanisms. So you need a secondary mechanism or a different mechanism to actually sustain that loop structure. And I'm going to skip this bit and focus on one or two more ideas that have been going around the last few years. So where does that leave us with wave heating? I think what it mostly tells us is our models were too basic, and people have started looking at different aspects. And let's focus on this cartoon at the bottom here. So we've talked about this bit already. You get a transverse oscillation of the loop. Because of resonant absorption or mode coupling, you excite these kind of azimuthal motions in the boundary layer. But this then, because you have a shear at the boundary of the loop now with the external environment, can excite the Kelvin-Helmholtz instability, which will deform the edge of your loop, enhance the creation of small length scales, which might enhance the heating rate. And this is a simulation from Patrick Antolin. Let me just drag it all the way to the start. Okay, so he starts with that uniform density shell, and you can see that very quickly you get this kind of stripy fine scale structure, or if you look at a cross section, again, you start with a density that's smooth at the edges, but very quickly you see all these Kelvin-Helmholtz vortices develop at the edges, and you'd get very small current sheets, which again, I'm sorry, is hard to see, but you get this very small scale current sheets throughout the loop. And we have one more topic that I would like to highlight, which was done by colleagues in Leuven last year. And that's again looking at the idea of whether you can create small length scales by making more detailed models, essentially. So what they started with is, again, this is a cross-section through their simulation of density structure. Okay? So not just a density cylinder this case, but a collection of very thin strands. And they then have a wave propagating in from the bottom. And what happens is that very quickly you'll get a lot of mess, essentially. Okay, so you get a lot of fine scale structure. And they looked at this in detail, and there's only a propagating wave coming from one side. Only one boundary of this domain is being driven. But because of the transverse density structuring, they found that in situ, and this is kind of complex, it's not a counter-propagating wave that is generated, but a co-propagating, downward propagating wave. Okay, so they generate the upward propagating waves, and they found that the transverse density structuring automatically generates a downward propagating component that travels with the upward propagating wave. And they coined the term uniturbulence for this. Now, what's important here again, and that's in the second movie here, is that as this process happens, you again generate a lot of very small scale distributed current sheets throughout the volume where heating can take place. Okay? So these are still wave-based heating mechanisms, but taking it a step further than the basic resonant absorption and phase mixing models that we saw at the start. Now I'm going to look at the chair whether I should go to the conclusions or not. I'm going to go to the conclusions. Okay, what would I like you to take away from this talk? Well, first of all, that our observations have shown that there's MHD or wave power present throughout the solar atmosphere. Okay, so theorists, modelers, including myself, have turned their attention back to these MHD wave heating mechanisms and say, well, actually, what do we do with all this observed wave power? Is this a mechanism for heating the solar corona? And the answer here is maybe, possibly, okay? We've got a lot of problems, and we're having to work hard on our models. Now, I told you at the very start that I was only talking about wave-based heating mechanisms. That doesn't mean there aren't any other models, okay? And for the moment, at least within active regions in the sun's atmosphere, I actually think that non-wave-based heating mechanisms are less problematic based on current models. And I'll finish there. Thank you very much.
Thank you very much indeed. Sorry to pressure you for time.
That's okay.
So, open for one question, I think.
Quickly.
Okay, I have one. Is there a real kind of killer observation, regardless of what instruments can now do, but what would you really like to see on these 2 to 3 million solar satellites which are going around the sun at the moment? What is the observation that might really clinch this?
I don't think we know that yet.
Yeah,
and I think that's really where the models have to focus.
Right.
Is there actually a signature that will allow us to say, that's what the heating mechanism is? And I don't think, I'm looking at the back row where my solar colleagues are residing, I don't think we've got it yet. I think there are hints in some of the very high temperatures. but I don't think we quite have a definitive observational signature yet.
So the one polite question I want to ask.
I hope I haven't just killed off all our funding.
Okay, but thank you very much.
Thank you very much.
Thank you.